So in the last couple chapters, we looked at integrals along lines and over regions, and then we saw Green's theorem, which kind of related the two of them. Now we're going to take the whole thing up another dimension, and we're going to look at integrals over surfaces and over solid regions, and look at theorems that relate those two. And this is of more interest because, hey, we live in 3D, right? So we got some cool pictures, some gnarly formulas, but some cool pictures for you. So let's see. So I'm going to start off with just the idea of the parameterization of a surface in R3. So this is going to be a mapping from R2 to R3. And so we've got an X coordinate and a Y coordinate and a Z coordinate, but each of these can depend on two variables. And I'm indicating here that sigma is a mapping from all of R2, but it doesn't need to be. It might just have a domain that's some subset of R2. So for instance, this guy over here, we're just restricting to some nice domain, and notice here that this is the UV plane that we're mapping from, and we're going into good old X, Y, Z space, right? And so you can imagine that maybe if there was a line of constant V, so this is like where V is equal to some constant value, then that's going to get translated into one of these kind of curves like this. And if you have some line of constant U, so maybe this is where U is fixed equal to some value U naught, that would correspond to one of these grid lines like that. Okay, so just sort of thinking about how to visualize a parameterization of a surface in terms of images of coordinate lines like we've seen before. So now if we have a function and we want to look at the graph of it, so if a surface can be understood as the graph of a function, then there's a natural parameterization. And so what we do is we just say, okay, so our sigma will take X and Y to be the parameters, and then we're going to map it to the points in 3 space where the first coordinate is just X, the second coordinate is just Y, and the third coordinate is F of XY, right? And so then say we have fxy is x squared plus y squared plus 1. Then the graph is going to look like this guy. So here you can see we've got the x-axis is going this way and the y-axis is going this way, just as usual. And if I fix a y value of some curve like this one here, then that's going to be, if I look at then sigma of x comma and then our fixed y value, maybe this is where y is equal to c, then it's going to trace out that curve above it. And if I were to fix some, here's where x is equal to a, then if I look at sigma of a comma y, as y varies through the domain, then we get some curve up above it like that.